you could have vibrational states.
So the reason why you said that was because the potentials being not symmetric at low V levels is not likely to have equality of inches.
It's not likely to have
only when your force increasing and by chance you would see.
Yes, that is exactly.
The other question I have is, see at high laser fields.
Yes.
In an experiment, I would probably have multi-photon processes going on.
Yes.
How is that worked and how is
Now the question is the description of multi-photon processes. Usually, the way multi-photon processes are described are in terms of perturbation field.
Yeah, no, I'm just looking at the experiment. Supposing I shine a strong laser field
and you have
multi-photon process going. So how do I suppress the multi-photon process and see this dressed atom chemistry going on?
See, the only possibility is probably to increase the frequency and intensity of the laser such that
so you're
don't see it.
beyond the realm of multi-photon
yes.
process.
Yes.
Can we keep on squeezing the atoms if we use pulse laser?
Now, a pulse laser, yes. But what would happen is, at the beginning of the rising edge of the pulse, you would have ionization. Precise, very precise ionization. Now, a pulse laser, and then the ionization does not happen. In fact, at the peak region of the pulse. Now, yeah, that's probably what you wanted to go with. Yes, you can keep squeezing it.
You had helium diamond.
Yes.
Supposing you took helium-4 and helium-3.
Yes.
Does the nuclear spin statistics come and interfere with this whole process?
I have not would it actually do it in an experiment? No. I don't think so because the laser coupling, the major coupling of the laser is a dipole interaction. I have not considered the magnetic field of the laser at all. In fact, those effects would be weak. So most probably, I would think that the spins will not have an effect, but I am not sure.
No, the reason I'm asking this question is because once you have bond potential, you have both vibration and rotational levels.
Yes.
Rotational levels, the very existence or not would be dependent on the boson or the fermion nature of the species. Therefore, is that going to completely alter the chemistry that we would probably see in these situations?
I don't think so. I don't think so because the reason why I'm saying is that the chemistry is basically driven by the electrons. The electrons are completely driven by the laser in this particular case. In fact, suppose you did not even have the nucleus, even then you would have a stabilized state which is called a Wolfram state. Just the oscillating field would stabilize bare electrons. In fact, there also have been speculations. If you take two bare positive charges, you take it in a circularly polarized state, those are going to remain stable after overcoming the Coulombic force of gravity. The reason is it's the whole thing of confinement by the laser.
Using this technique, is it possible to reduce the decay time of radioactive?
Yes, radioactive elements, decay time of an electron, yes. Decay time of an electron in the sense the electron is not going to last. But now, I would have to use some other process probably to decrease the decay time of. Not a laser.
I don't think there's anything you can do to tamper the decay time of radioactive nuclei.
Something which goes against the strong forces. Some confinement.
Don't know.
Yes, of course.
The double well is found only in the case of linearly polarized lasers. Yes. In fact, that is something else which we also want to look at. So, helium atom in a circularly polarized laser field. There is interest for helium atoms in a circularly polarized laser field because of this particular effect which I told you. If you have a laser pulse which is circularly polarized, at the rising edge of the laser pulse, you have very precise bursts of ionization. And using this, people are trying to construct something which is called Atto clock. So, in fact, this particular thing about helium in a circularly polarized laser, including ionization effects, is something which we want to work on. Now, elliptically polarized case, you again would have a different kind of symmetry. In fact, it would not be something like a diatomic molecule, but you will have it in all particular directions, right? So instead of just a line changing, we will have the symmetry. See, the system would follow the symmetry of the laser completely. Yeah, that is something I do not know. Probably at very low temperature. It has to be at very low temperatures. In fact, there's a laser.
If you went to supersonic expansion, you can see helium diamonds.
Yes.
People have seen that.
Yes.
But then that's probably the diamond that's supporting one vibration level or whatever. Because the temperature is millikelvin or
Yes.
fractions of Kelvin. So if you took the helium 2 diamond in a supersonic expansion, applied the field, then suddenly you have got this huge potential.
Yes.
And now you can excite this helium
Yes.
diamond into higher vibration level.
Actually, this.
And if the field is not removed, then that level has no meaning, and therefore it should be equal to free dissociation or something.
Yeah, actually that is true, but I do not know if you would be able to create it in more number of helium atoms.
That's true.
If you keep taking more number of helium atoms. Yeah, this particular helium dimer, it's just an initial thought experiment in the sense. But the natural way to go about it is to increase number of helium atoms. It's a very, very simple calculation, the way we have done it, which you probably realize. So we can actually go to more number of helium atoms. Only thing is we have to be careful about dipole approximation, size of the system that you take, so on and so forth. We have to be careful when we do it.
If there are no more questions, let's thank Dr. Balanarayan once again.
Thanks.
That closes the Curie activity for the semester.
That's right.